Okay, so we're going to make a start, and today we're going to continue on with talking about multithreading, which we spent a lot of time on Monday talking about the concepts of. And where we finished off on Monday is we're looking at atomic operations. And we're looking at the atomic operations library and for atomic types that are available in C++11. And the purpose of the atomic types was basically that we avoid race conditions, or we avoid issues whereabouts we hit critical sections of code, for instance, incrementing or decrementing a number. And if you're doing that in parallel, those numbers being inconsistent because two threads have modified a number at the same time. And we looked at this example whereabouts we used an atomic number to have one thread incrementing, one thread decrementing, and how this worked and always got us out for number one. But the problem with this code is we had some performance issues, so in particular using the atomic operator slowed down the code because I had to synchronize through locking all the time. And we talked about how you structure multi-threaded code has a large influence on performance. And we left with the example of still using the atomic int I up the top, but we've introduced some local memory and some local variables to do the calculations on each thread, and then only once the result is calculated does it actually go and modify the global shared memory. And that's where we got up to at the end of Monday. And today we're going to be picking up and we're going to be continuing on along this path. Now, one question that happened at the end of Monday's lecture was someone said, well, now we're only reading to and writing to that global shared piece of memory once. Why does it need to be atomic at all? It still needs to be atomic because you could still write to it at the same time. So it still definitely needs to be atomic. The difference between two slides previous, so this version, is this version has 2 million writes to that shared piece of memory. This one has only 2 writes to this shared piece of memory. So performance-wise, and as we showed on Monday with the live demo, performance-wise, the second one is much, much, much faster than the earlier version. Now, this atomic library is nice because we go over back to here and we can see that we have some atomic bills and some atomic chars, ints, unsigned ints, longs, etc. And you'll see that the full specialization makes this thing look like it's a templated type, but like a vector. So could we create just an atomic Euclidean vector? Could we just create an atomic graph? Can we just wrap atomic around normal data structures and just have that all work really nicely for us? Well, unfortunately, the answer to that is no. Okay? So the standard atomic library does not provide much support at all for creating atomic wrappers around your own data types. Now, if you write what's called a trivially copyable type, T, which has no user-defined copy controller, so no move semantics, no copy assignment, no default constructors, no destructors, etc. If you just write what is called a trivial copyable class, which is simply, you can also think of this as just being a plain old data type. So something that there's just data, there's no methods to manipulate these types, everything's public. You can wrap atomic around there, but that's not particularly good design. And atomic classes can wrap raw pointers, not smart pointers. They can wrap raw dumb old pointers, but they cannot wrap what those things dereference to. So the atomic classes, except for atomic int when need be, are not actually that useful to us. Okay? They solve our problem, our very simple problem over there of incrementing and decrementing, but they don't particularly help us out when we start to deal with our own classes. And even if they could help us out with synchronizing on our whole classes, imagine they could, this actually still wouldn't be a very good thing for us to be able to do, because synchronizing across a whole class, so having one thread only be able to access an entire object. So imagine if we synchronized on our graph class. Imagine we had a huge graph container and we synchronized or atomic atomic locked that whole graph class. That means that only one thread at any one time could access the data or modify the data in that class. And that class, that object, might be huge. It might have hundreds of different methods, might store thousands of different things. And surely you'd only want to find the critical sections on very small, little important areas of that class, not the whole thing. So even if we could wrap, and we can't, but even if we could wrap atomic around a whole class, it's not really particularly good. It defeats the purpose of multithreading. So how do we sort out our classes and sort out our code structures to only wrap or synchronize or lock on critical sections that are only in certain methods or across a whole method or across very small objects? How do we do that? Well, we talked about the concepts of mutexes on Monday. And the general idea is that you have a thread that wants to read or write some shared memory. Okay, and this is a bit of a revision for Monday. So we want to read or write for shared memory. So we try to lock a mutex object that guards that object, or a piece of critical section. So we've got a mutex object that's guarding that piece of critical section, which can be memory, it can be objects. It depends exactly what your code's doing, what that critical section is. And if another thread is currently locking the same mutex first, the first thread waits until the thread is unlocked and then grabs that mutex and keeps continuing. Or in some mutex objects, there's a timer that expires. And if the timer expires, you just go off and do something else. So you don't want your code waiting for 1,000 years for some mutex to be unlocked. You just go, okay, well, I'm never getting control of that object, so let's either print an error message or let's go do something else. Now, when a thread obtains a lock, it can safely read or write for shared memory based on the assumption that everyone else is using the same mutex objects. If everything isn't using the same mutex objects, you've got massive problems in your code. And when a thread releases or is finished doing something with that shared memory it's got the lock over, it must release the lock. If it doesn't, again, your code can potentially crash. Best case scenario, your code crashes. Worst case scenario, you end up with a deadlock, which is your code just keeps running forever and never terminates. And it's important to note that if 2 or more threads are waiting, so say you've got 3 threads, they're all dealing with the same critical section. If 2 or more threads are waiting for a lock to be released, there's no order in which they'll obtain the lock next. So it's not first in, first served. They're all waiting for the lock. One of them will get the lock on that mutex object, and you don't strictly know which one it's going to be. Okay, and like I pointed out, it's assumed that all threads are using the same mutex object to correctly access the shared memory. So we have this standard mutex type, and it's a non-timed mutex class. Okay, that means it doesn't have a timer available for it. There is mutexes with timers. And so it has some member functions. Standard mutex, it's got lock, which tries to get the lock. If it can lock it, it locks. If it can't lock it, it blocks, so it waits indefinitely until it can acquire the lock. You have a member function try lock, which is try to lock the mutex. If you can't, just immediately return false and keep going. Okay? So bad piece of code. Do not just do try lock, oh, that didn't work, and go into the critical section anyway. You should wrap for try lock in an if statement or while loop or something like that. And of course, unlock releases the lock that's currently held. It's important to note if you're doing recursive functions, you need to use a thing called a recursive mutex. The reason why you need to use a recursive mutex, because if you're in a thread, think about this, okay? I am thread ID 1, okay? I have a recursive function inside me, and I use a standard mutex. Inside this recursive function, I call lock. I then recurse. When I recurse, so I call the same function again, the same function again attempts to call lock a second time. What happens? It's not going to be able to because somebody's already locked the mutex. Okay? So if you're doing recursion, you need to use a recursive mutex. So we have an example of how this works. And this code is very similar to what we had before. Okay, actually, it's so similar to what we had before, and I'm not even going to run it. I'm assuming you know it's going to work. And so what we have is we're back to our int I, so we've lost our atomic variable. We're back to just a standard int I. We've created this mutex object. Okay, and this mutex object is looking after our variable I. That's why I call it iMutex. Before we go and modify the value of I, we lock it, and once we've modified the value of I, we unlock it. Okay? And so you can see here, this thread 1 goes and locks mutex, or waits for it to be locked, and thread 2 also locks mutex, or waits for it to be locked if thread 1's already got it. And hopefully everyone can see, I will run this code if I have to, but hopefully everyone can see that the output of this is just going to be 1. And this is thread safe, this is memory safe, there's not going to be any issues with this code. Can everyone see that? Yep. So despite this all being good, what's the problem with this code? So despite this code running, it's always going to get us the right solution. What is the problem with this code?
It's just as inefficient as when you're using the atomic int.
Yeah, it's exactly the same problem we had with atomic operations. Okay? So if the standard mutex takes exclusive ownership over the objects, our program slows down while the threads are busy waiting to acquire the mutex lock. So busy waiting just literally means that I am waiting for something to happen and I'm paused. And depending exactly on your CPU architecture, that may or may not actually use CPU cycles. Okay? Busy waiting is what we want to try to avoid. Okay, so we've got this issue of exclusive ownership of a lock over a critical section is required for safely writing the data. Okay, so we need to acquire that lock for safely writing the data, because if two things attempt to write the data at the same time, we end up with the same problem we had on Monday, whereabouts the data gets corrupted. Okay, but what about reading it? What about reading the data? Surely two threads should be able to read the data at the same time. Because they're not writing it, because they're not writing the data, we should be able to be fine with that. And so the idea of having to get a lock just so we can read data seems a little bit like a waste of time, quite literally a waste of time. Okay? So going back to theoretical ideas of how multi-threading works, we've just looked at locks, and basically just really simple mutex locks about you want to access something, you lock it. You unlock it once you've finished dealing with it. A thing called a reader's-writer's lock has multiple ways in which it can be locked. Okay? And so what it does is the reader's-writer's lock allows multiple threads to read data in parallel. Okay? So these multiple threads can go and lock the same mutex. They can lock the same mutex in parallel. Okay? But if data needs to be written, then exclusive ownership over mutex must be acquired, which means that multiple threads can all go and lock a mutex and say, I'm reading this data, but in order to write to the data, they need to acquire what's called an exclusive ownership, and they might have to wait for all these other threads to finish reading the data and unlock their reader's lock. Okay, so there's two locks involved. There's a reader's lock, there's a writer's lock. For reader's lock, multiple things can lock. For writer's lock, only one thing can lock, and the condition on the writer's lock for it to be able to lock is that all the reader's locks have to be released. And in C++14, so not C++11, so in C++14, there's a thing called a shared timed mutex. It's a form of a reader's-writer's lock. So the shared ownership idea, so a read lock idea is you lock shared, and this blocks until the read lock is acquired. Now, normally the read lock would be acquired immediately, but the read lock will not be acquired if the writer's lock has already been acquired by something else. So if somebody's already writing data, the read lock is waiting until that writing lock is released, and then it can read the data that's been written. And so, like I pointed out, multiple threads can lock this shared lock at the same time in parallel, and they can read it like that. Exclusive ownership, so the write lock, is just the standard lock function, so the same as we saw on the standard mutex before, and that blocks until the write lock is acquired. To acquire the write lock, both the read and write locks need to be unlocked by everything else before that ownership can be acquired. While a thread has the exclusive ownership, so that's the writer's lock, no other thread can obtain any lock, so read or write. And when you're unlocking, you have to make sure you unlock the correct lock. If you have the reader's lock, so if you've got the shared lock, you must unlock the shared lock. If you have the writer's lock, you must unlock the writer's lock. If you do these wrong, again, best case scenario, you get some nice error message. Worst case scenario, you will end up somehow deadlocking your code. Okay? So again, these are fantastic tools that you can use to increase the performance of your code and do amazing things and fast things and cool things. However, with great power, it's up to you guys to use it correctly and make sure your code doesn't have bugs in it. Okay? And we're going to talk about bugs in a few slides' time to do with mutexes, because mutexes can lead to a lot of bugs. Actually, no, it's the next slide. It's the next slide. Okay, so take a look at this code. Take a look at this code. I don't know if I got the demo for this code, but I'll take a look at it if I do. So can someone tell me what the bug in this code is? So there's an exception being thrown. What's going to happen in this code? I don't have the live demo of it. So this is the same code that we've seen already. Okay, it's got int I, it's got the mutex I, it locks the mutex, it unlocks the mutex. This one plus pluses, this one's minus minuses. Okay, now we've introduced this if statement to say we can't decrement I below 0 because, say instead of this being an int I here, say this was an unsigned int, and we didn't want to decrement I to below 0 because if we decremented I to below 0, well, an unsigned int means it will wrap to max int and we'll have a whole lot of problems. So we've got an if statement saying that I cannot be less than 0 and we throw an exception to do that. What's the problem?
The lock will remain because you don't execute the unlock instruction.
Yep. So once we throw, the unlock doesn't happen, so what happens next? Deadlock. We have a deadlock because this doesn't get unlocked. Up here, it will attempt to acquire the lock, it busy waits until it can acquire the lock. It's never going to acquire the lock because that thread has thrown an exception, so that thread is finished, it's dead, it's gone. It's down here on line 24, 25, control return to main. So main is also busy then waiting for T1 to finish. T1's never going to finish. We have a complete deadlock in this situation. Where have we seen this sort of problem before? Not necessarily in multi-threading, but where in this course before have we seen this problem? Sorry? In the try-catch section, yeah. But what in particular have we seen this before? Pointers. Sorry? Pointers, yep. So what about pointers in particular have we seen this before? What about pointers? In what situations using pointers have we seen this before? Yep. Yep, so we've seen this in stack unwinding with try-catches and dynamic memory. And so what we saw with dynamic memory is if you're using new and delete, and you create something new, and you throw an exception, and your delete is in the code below that exception, and that delete never occurs, you have a memory leak. I'm hoping everyone would remember this because I'm pausing on this because there's a question in the exam about this. There's a question in the exam about stack unwinding, there's a question in the exam about dynamic memory and dynamic memory leaks. Okay? That's not the entire answer to the question, but it is a part of the answer to the question. So, we've seen this problem before. We've seen this problem with dynamic memory. This isn't dynamic memory, okay, so we don't have a dynamic memory leak, but we've got a very, very similar problem. How did we fix this problem with dynamic memory? Smart pointers. So with the dynamic memory, we fix this problem by basically going, we're done, we're going to write buggy code, so let's write some smart pointers. And smart pointers encapsulated the idea that resource allocation is initialization. So a smart pointer object wraps around that dynamic piece of data, takes ownership over it, so this idea of ownership, it takes ownership over that data, and so it can manage that either in a unique way, so a unique ownership is the thing goes out of scope, it gets destroyed because of the object being destroyed, or shared ownership through shared and weak pointers with reference counting. Again, you should know these for principles of idea of reference counting and how these things work for the exam, but that's another story for another day. Let's keep looking at this though, okay? So we've got this problem, we've got these mutexes, and mutexes in terms of this code are working in a very similar way to new and delete and dumb raw pointers. They're introducing this problem whereabouts mutex hasn't leaked, but our mutex has deadlocked. So this is basically the summary of what I've just said, okay, with a point of even if we catch the exception, if the mutex isn't unlocked in the exception catching, deadlocks or undefined program behavior may occur. This is even worse because say if we threw the exception before we locked the mutex and then we attempted to unlock a mutex that we hadn't had locked in the first place, that's also going to cause us grief. So this is full of problems. Full of problems. This is how we fix the problem. Very simple. We still have our mutex. Okay, the point I need to make is we still have our mutex object. Okay, we don't get rid of the mutex object, but we create a thing called a lock guard. And the lock guard protects our mutex. Our lock guard is essentially the same principle as a shared or unique pointer over a pointer. This is a wrapper around for mutex. Okay, so wrap around mutex. And as you can see here, I don't have the word lock in terms of calling the function to lock. I don't have the function called unlock. Basically, the lock guard takes ownership over that mutex when it gets created, and then when that lock guard goes out of scope, either through going out of scope normally or getting thrown out of scope, it will get destroyed, and when it gets destroyed, the destructive of the lock guard unlocks the mutex. Okay? Same idea as smart pointers. Now, that's, again, basically what I just said on that previous slide looking at the code. So, lock guards are exception safe. Okay, lock guards are exception safe, and they work essentially exactly the same way as smart pointers do. And you should never manually lock or unlock a mutex. You should never manually lock or unlock a mutex, always use the lock guard. Okay? Now, if I jump back to the side here, just be aware of looking at scope of these things. The mutex up here is in shared memory. Okay, the mutex is in shared memory. The lock guard is in local memory. The lock guard's in local memory. And actually, I'm going to bring this one up on the screens. Yep. So I'm just going to switch to my laptop here. And I'm going to bring this up on both screens because this room doesn't like dual outputs. Let's see if this works. Okay, here we go. So this is the code, okay, that we're seeing. And so I'm going to make thread lambda lock guard. Okay, and that makes, and I'm going to run it. Okay, and that returns 1. That returns 1. Now, like I was pointing out, the mutex up here, this is shared memory. This lock guard in here is local memory. Okay, and that lock guard there on line 11, and this lock guard here on line 17, they're 2 different lock guards and 2 different objects on 2 different threads. Okay, because this up here is start of thread 1, and this down here is the start of thread 2. Okay. Now let's just say that I don't know, as someone doing this course, I'm not quite sure how these things work. Okay? What happens if I'm not quite sure about these lock guards? So I've been told that for lock guards, I always need for lock guards. Okay? Always need for lock guards over my mutexes because I shouldn't manually lock or unlock my mutex. And so I'm trying to write some efficient code, and I go, well, look, the mutex is there, so maybe when I create for mutex, I should just do the lock guard at that point. What's going to happen to this code? Yeah, okay, so the lock guard is going to lock the mutex on line 9, and it's going to release it when main goes out of scope. So first of all, we've moved what thread has control over that lock guard. Okay? But before I run the code, what's going to happen in this code? What do people think the output of this code is going to be? Who thinks the output of this code is going to be 1? Who thinks the output of this code is going to be a deadlock? Oh, my tutor thinks it's going to be a deadlock. This is going to be fun. Who thinks it's going to be for same race condition or same problem that we had earlier? Some of you. Let's find out. Okay, so it compiles. Oh, yep. We're back to the same problem that we had on Monday. So we've done the right thing. We've created mutex. We have put a lock guard around it. And everything is stuffed up. Okay? Because we put the mutex simply in the wrong place. People looking confused. Do people see what's going on? Yep. Any questions at this point? Okay, if not, we're gonna move on. We've got it's going to get more complex. So I just need to make sure you guys are understanding what's going on. Okay? So we have the mutex objects. We have the lock guards that protect the mutex objects, but the lock guards have to be put in the right place, or else you defeat the point of using them. Okay? What happens if I put the lock guard outside of a for loop at each of the local ones? What do you think is going to happen? It should work, but what do you think is going to happen? Okay, so we'll do this again. We'll do this again. I'm not going to compile this until we work out what we think it's going to be. Who thinks the output's going to be 1? Most people. Who thinks the output's going to be for race condition that we had before? Who thinks the output's going to be deadlock? Okay, we've got a couple of people think it's going to be a deadlock. I'm putting my money in the number 1 camp. Okay, I'm putting my money in the number 1 camp. And it's number 1. Okay. But let's talk about the performance of this one. Did I say it's not multi-threaded? It's still multi-threaded. But what's happening?
You're only running the 1 forward.
Sorry?
You're only using the 1 forward. It's just increment all the way up, and then it'll unlock, and then the second row is slightly different, and then the second way is forward.
Yep.
And so all the way down.
Yep. So the code definitely is still multi-threaded. But basically, what you've done is by gaining the mutex at that start of that thread right there, is you've gone, okay, I'm going to lock and I'm going to run this whole thread. And the other thread has to wait for all the calculations in that first thread to finish before the second one happens. Again, scope, incredibly important. That for loop, every time around that for loop, that lock guard is being destroyed and recreated. Okay? So in terms of performance, for this particular example, you may actually find that this version is actually faster than the other one. Okay? Because you're not tearing up and tearing down that lock guard all the time. So for performance, you actually might find that this version is faster. Okay? But this is not good code. And the reason why it's not good code is because this is a toy example. We're doing plus, plus, and minus, minus. If this math was much more complex math, that performance loss in terms of tearing up, tearing down the lock guard is minute compared to what other calculations you could be doing. Okay? So this is my point. Scoping, knowing where the lock guards go, is important. Okay? So lock guards, they cover off for issues that we have with mutexes going out of scope, and to a certain extent, some deadlocks occurring. Okay? But now I'm going to show you how we can still end up with deadlocks with lock guards. Okay, let's see if these screens come back up. Here we go. Okay, so let's look at the scenario. Let's look at the scenario, and I'm not 100% sure I've got the code for this one. So we have a struct, okay? So I like fast code, okay? So all this multi-threading stuff, you're going to see a lot of structs rather than the classes. So I have this struct of a box. The box has a counter to tell you the number of things that are stored inside the box, okay? It has a constructor to make a box, and the constructor takes in the number of items, and it also has a mutex over the box itself, so the mutex can modify the number of things that are inside the box. Okay? Now, imagine we have a function that transfers items between two box objects. Okay? And so remembering that each box object itself has a mutex on it. Okay? We have a function here to transfer items from box 1 to box 2. Okay? And so we give it the number of items that we want to transfer, and so we've got box from and box 2. Okay? We acquire the lock guards over those mutexes for both boxes. Okay? And then we go take a number of things from box 1 and put a number of things into box 2. Okay? Now imagine this code is more complex. Again, toy examples are fun, but imagine that this was more complex, so it actually was transferring physical things and not just numbers. Now, here's a problem. What happens if two threads in parallel attempt to move between the same two boxes in opposite directions? So I've got box A, box B. I say transfer 10 items from box A to box B. If it's exactly in parallel on a second thread, I say transfer 15 items from box B to box A. What happens? I will have a deadlock like the one I showed on Monday. Why do I have a deadlock?
Because one thread will try to acquire box A first, and then box B, the other one will be acquiring box B first.
Yep, so this is exactly the same problem we had on Monday. The code comes in, line 2 of this code locks for from with the lock guard. Okay? And so one of them is going from box A to box B, one is going from box B to box A. So one of the threads locks box A, one of the thread locks box B, and then they go to lock. The first thread tries to lock box B, once it already locks, it waits. The second thread tries to lock box A as well. Box A is locked, so now we've got a deadlock. How do we solve this? Okay, so this is the code to do it. I must have actually written the code up to do this at some point, okay? I don't actually have the live demo of this, but this is the code that would deadlock, okay? So here's our main. We create box 1 with 100 items, box 2 with 50 items. We attempt to transfer 10 in one direction, and we attempt to transfer 5 in the second direction. The standard ref stuff, ignore that kind of for now. You might need this in your code. It basically ensures when you're transferring things across multiple threads that the references are correctly handled. And so what I mean by that, if you go back and look at this transfer function, you see how this is taking references, not values, up there? Okay, standard ref nicely sorts that out. It's a minor point, but you might need to discover that when you do assignment 4. I don't think my code uses standard ref, but it's a side note, okay? So all these slides here are designed to help you out with thinking about stuff for assignment 4. There's lots of different ways of doing assignment 4. Your objective for assignment 4 is just make it go as fast as possible and not have memory corruption issues and deadlocks and things. So we've got this issue. We're about to be in a deadlock. And so C++11 again helps us out a little bit more. C++11 helps us out a little bit more by having yet another type of lock. Okay? And so we have these lock guards, and these lock guards are designed to prevent issues with mutexes going out of scope not being unlocked. Okay? So lock guards are designed to help us out. But then lock guards can still get into deadlocks. Okay? So a unique lock is a lock guard, but it's a more complex lock guard. And so a unique lock allows us to wrap a mutex in a lock guard, but not lock immediately. Not lock. So we defer the locking. Okay? We defer the locking until we say, okay, we're ready to lock now. And so we can use this code to create a unique lock around our mutexes inside our transfer function. Okay, so we lock mutex 1, we lock mutex 2. Okay? And you'll see the constructors here take what they're meant to be locking and the fact that they're a deferred lock. Okay? Then we call this function called standard lock on lock 1 and lock 2. And the way in which this standard lock attempts to work is the standard lock attempts to lock lock 1. If it can't lock lock 1, it backs off and waits until it can lock lock 1. If it can lock lock 1, it attempts to lock lock 2. If it can't lock lock 2, it unlocks lock 1 and backs off until it can lock lock 2. Repeat. It then attempts to lock lock 2. Okay, good, we've got lock 2. Now I'm going to attempt to lock lock 1. Okay, good, I've managed to lock lock 1. We can continue. Else, back off, keep trying. Back off, keep trying. So it attempts to avoid deadlock by grabbing the lock for one of the things. When it goes to attempt to lock the second thing, if it can't get it, it releases the first. Okay? So unique lock and standard lock and these deferred locks are techniques for trying to avoid deadlocks. Not the be-all and end-all of how you avoid deadlocks. Avoiding deadlocks is very, very, very challenging. Very challenging to avoid deadlocks. Okay? But C++11 gives you a number of tools available to do so. Okay? Yep, question.
How many locks can we put in the standard lock?
How many locks do we put in the standard lock?
Yeah, can we put a lock 3? I mean, if we have one.
I don't know. You would need to go look it up on the reference guide. So you'll see a lot of these slides whereabouts I've got a lot of these sources from. Like I mentioned on Monday, a lot of this content has come out of this book called Professional C++. Other examples have come from cppreference.com, and other examples have come from another website, which I'll put the links up to. But if you go right to the end of here, you'll see a link to this website here. And this has a number of blog posts about how to use these threading libraries. Also note that a number of these slides, where it's clearly labelled, some of them are labelled up at C++14. Like I said, I haven't given out assignment 4 yet. I am having a debate with myself about whether actually I'll get you guys' opinion on it. I am willing to make assignment 4 standardized on C++14 rather than standardized on C++11 if you guys are comfortable doing that. C++14 gains you readers and writers locks and gains you a little bit more in terms of what you can do with the threading libraries, okay? The challenge with C++14 is it's not 100% supported by all the compilers. And so that means you have to be very careful to make sure you correctly test your code on the school systems, even more than you test your C++11 code. Okay? So, do people want to give me their opinions on that? Who would like to do C++14? A couple of people. Who would only want to do C++11? Okay. That's easy. C++11 wins because it's in the course outline. Okay? So, C++11 is going to be the winner for assignment 4, so that means you'll have to make sure it runs under C++11 style techniques. Okay, my code is C++11 compliant. What happens if it's too complex to set up the marking system to do that, unfortunately? Okay, so the marking system does not like being able to switch between these things. I'll think about this some more though. I'll think about this some more. I haven't written up the spec completely yet, but with assignment 4, you shouldn't need the C++14 stuff, but I'll take a look a little bit more into it. Okay. At this point, I've got 10 minutes, okay? And I'm not going to get through the next section in 10 minutes, okay? So I'm gonna basically stop now. What we're working towards, and we'll do this on the Thursday after the break. So next week is mid-semester break. Next week's mid-semester break. The Monday following mid-semester break is Labour Day, it's a public holiday. Okay, so there's no class on for Monday following mid-semester break because it's a public holiday. And so we have a Thursday lecture. We have a Thursday lecture of week 10, which will finish this off at that point. We then have week 11, which we're looking at object-oriented programming. We have week 12, which is a combination of catching up on anything we haven't cleared off, maybe doing some advanced topics. There may be a guest lecture in week 12 looking at some boost libraries and things like that. Because we lose the Monday lecture in week 10 due to Labour Day, there is a Monday lecture in week 13. It's already been booked in. The Monday lecture in week 13, and that Monday lecture in week 13 is when we'll talk about for exam and talk about revision and things like that. Again, given I've got 7 or 8 minutes, I might as well talk about briefly the exam content, exam structure at this point. Not sure if you guys have seen it yet, but for exam timetable, at least the draft timetable, is out. The exam for this course is on Tuesday, the 17th of November in the afternoon. It's a 3-hour afternoon exam on Tuesday, 17th November, which is, I think, the second, possibly the third week of exams. Like I said, it's a 3-hour exam. It has, it's worth 50% of your course. It's compulsory pass, so you must pass the exam to pass the course. Passing the exam to pass the course means that that pass happens after scaling, okay? So the exam will get scaled. The exam, and we'll talk about this more in week 13, but the exam is structured with 40% of the content, so 20 marks, 40% of the content is short answer, and then 60% of the content is longer answer. And what I mean by short answer is, so there's 20 questions, there's 20 short answer questions. 13 of those are multi-choice. Okay, there's 13 multi-choice questions. There's then 7 short answer questions, and those 7 short answer questions are, here's some code, what is the output of this code? And those sort of questions will be literally going back up to something like this and asking you what the output of this program is, okay? And clearly the output of this program is 1, it just might take you some time to read through that, okay? That would be probably the longest one of those types of questions that you'd get, and unfortunately, no, that is not the question that you're going to be given. Okay, so 13 multi-choice questions, 7 short answer, reading some code, what's the output? Then 30 marks, or 60% of your exam, is longer answer questions. And these questions range between 1 mark and 3 mark each. They're arranged into sections, so there's I think off the top of my head, again, we'll talk about this more in week 13, but there's about 4 or 5 sections that constitute that next area. 10 of those marks, or 12 of those marks, are based on core C++. So knowing the difference between L values and R values, knowing the difference between call by value, call by reference, knowing the difference between heap memory and stack memory. Okay? So knowing those sort of things. Then there is a section, again, short answer section, that will be on classes. And so knowing the difference between copy constructors and move constructors. Knowing how to do an operator overload. You will be asked to write a very short operator overload. So knowing how to write, maybe it's the equality symbol, it's not what I'm telling you, but maybe I'll ask you, can you write a short equality operator for this class that's given, okay? And it will be about 2 or 3 lines. It won't be much code. I'm not asking you to write a page of code. If you write a page of code, you're doing something wrong, okay? So for coding questions, will be very short, write these functions, okay? In addition to writing the an operator, there will be a question about writing a lambda function. Okay, there will definitely be a question about writing a lambda function. Then we go into dynamic memory, and there'll be questions in dynamic memory about why you use smart pointers versus raw pointers. What benefits do smart pointers give you over raw pointers? How can your code generate memory leaks? What do you do to stop memory leaks? Questions like that. Then into templated classes and stuff like that. There's not a huge amount in terms of templated classes in the longer answer sections. They're more covered in multi-choice sections. But in terms of templated questions, there might be some questions about template specialization. There might be some questions about, actually there'll be a couple of questions about inheritance, which again we'll cover when we get to object-oriented programming. And then in terms of multi-threading, there's not much in the way of multi-threading. In fact, there's actually only 1 or 2 questions on multi-threading. And hint, hint, I kind of covered off what those questions might have been today in terms of, again, thinking about how mutexes can be used to protect code, but then how lock guards can protect mutexes, how probably not as complex as getting to unique locks and things like that, but thinking about how multi-threading can make your code faster, but how you still need to protect shared memory. Those longer answer questions will be, like I said, they're between 1 to 3 marks, okay? And they will consist of, some of them will be explain an idea, some of them will be write a very short piece of code. And when I say short piece of code, I literally mean there'll be no question that requires a piece of code longer than 5 or so lines per question. All up, you've got 3 hours for it. Like I said, it's worth 50 marks. It actually means you've got 6 minutes per question, roughly 6 minutes per question. So when you get a question like this, and what's the output of this? If this is taking you longer than 6 minutes, there's no way that it should take you longer than 6 minutes. So I expect everybody will be able to finish the exam within that 3-hour period. Yep.
Is it on paper?
It's handwritten. It's on paper. It's on paper, handwritten. The multi-choice questions is on the multi-choice. You've probably seen it before. The multi-choice, fill in the ABC card. The rest of the exam is on paper. Yep.
Is it at uni or the race course?
I've got absolutely no idea whether it's at uni or the race course. You'll find that out. Yeah, you'll find that out in the final timetable. Like I said, so the way in which the exam's set up is because you have to pass it to pass the course. There is the short answer questions. So those 40% questions. So the first section should be easy-ish. I'm not going to say it's easy, but it should be easy-ish. Some of our later questions, there's a few of them which are really quite tricky. Like they're not designed to trick you out or trip you up. That's what I really didn't like about previous year's exams. It was like, there's a bug in this code, go find this code. Go find the bug. I don't like those questions. If you want to do that, go use a compiler. But there is more theoretical stuff. So there's more explaining L values versus R values. There's more explanations of how that sort of stuff goes on. So you need to be on top of your theoretical side as well as your programming side. Okay. Any questions on the multi-threading at this point? If not, sometime next week, so sometime during the break, assignment 4 will be posted. Assignment 4 will be due on the Thursday of week 13. Assignment 4 will be due on the Thursday of week 13, so you've got plenty of time to do it. The reason why it's the Thursday is it just works with the late penalty applying out over the weekend, so we can mark that during StuVac and give the marks to you before exams start. Okay? See you in 2 weeks' time.